Previously, we learned how to differentiate series term by term, so it's not going to be a big surprise that we can also integrate series term by term, because natural integration is the opposite of differentiation. Previously, we had the following theorem that allowed us to differentiate term by term, so I'm going to change its wording slightly, and it will be a new theorem, but again, they're very closely related. So again, we're going to start with a given series with a given radius of convergence, and we're going to assume that the series converges to some function, and the statement of the theorem guarantees that this function will be integrable. So before it was differentiable, and now it will be integrable, and all of this will be happening on the same interval. And what I said previously about the boundaries or the series possibly changing its convergence at the boundaries remains true. So we're not going to be concerned too much about what happens at the boundaries, and to avoid dealing with it, we're just going to focus on the radius of convergence instead. Now, instead of differentiating here, we're going to be integrating, and I'm just going to rewrite the whole new statement here. So according to the theorem, the integral, of course indefinite integral of this function, can be identified by what we would call integration term by term. And of course, as you know, when we integrate, we have the constant of integration. Now, because we already used letter C to mark the center of the series, I'm going to use letter A. But this letter A is not just some constant, it's actually the first term of the series, naturally, because it doesn't have any power of x attached to it. So instead of writing this constant of integration on the right, I'm going to write it on the left. And A can always be determined by evaluating the function right at the center. So again, you'll see exactly what it means as we do an example, but this is the theorem that allows us to perform a term-by-term integration of some series. And let's do an example, and the first example will be for us to find the first 5 terms of the following function. This is definitely something that we haven't seen yet, at least not in the lectures, and it's absolutely non-trivial question that we wouldn't be able to answer if we didn't know this theorem. The theorem suggests us to look for some patterns and relations in the form derivative, antiderivative between this and some other function, and we're going to have to recall that derivative of 1 over 1 minus x, or rather, sorry, not the derivative of 1 over 1 minus x, but derivative of ln of 1 minus x is 1 over 1 minus x times the derivative of 1 minus x, which is going to be our starting point. So if we want to find ln of 1 minus x, the power series of ln of 1 minus x, let's consider the power series of this function. And it's going to be the negative outside. And again, this is a standard power series. And all of this is true on this interval of convergence. And now, what we've done previously we were able to differentiate both sides of this statement. And this time we're going to integrate. So I'm just going to copy this statement. And I'm going to add integral here. And, well, technically I'm putting it here because we're integrating the entire series. But the theorem that we just discussed says that I don't have to, or rather to integrate the entire series, I can just integrate it term by term. So on the left hand side we have exactly what we wanted. On the right hand side now we're going to differentiate it. So we're going to have, remember, we're going to have some constant of integration a plus, and we're going to write this out here carefully. We're going to have x to the power, we're going to have this minus here, or I guess we can keep the minus outside. And then the integral of x to the n is going to be x to the power n plus 1 over n plus 1. Now, to find a, we're going to plug in the center of the series into the function. So in our case, the function is ln of 1 minus x. So f of 0 is going to be ln of 1 minus 0, which is ln of 1, which is 0. So we don't really have to worry about this constant of integration. And finally, we're going to write this series with x to the n instead of x to the power n plus 1. So if we want to change that and have x to the n here, we would have to subtract 1 from all appearances of n's and add 1 right over here. So to summarize, the power series for this function would look like this. When n equals 1, we're going to have negative x. When n equals 2, we're going to have a negative 1/2 x squared, negative 1/3 x cubed, negative 1/4 x to the 4th, and so on. So this is going to be the pattern. And the radius of convergence for this power series to this function will be 1, and we don't know, or rather we don't want to know at this point, whether it converges at 1 and negative 1 or not. It's definitely not going to converge at 1, but yeah, so to avoid that whole dealing, we're just going to say that the radius is equal to 1. So we found the power series representation of a function which we didn't know before. Let's do another example. Let's find the power series representation for arctan of x. So how can we write this function as a power series? And we're going to have to also recall the following fact, that derivative, oh, we can just recall that the opposite, right? So the integral of some function with respect to x is equal to arctan x plus c. So which function is this? It's 1 over 1 plus x squared. So we can start with this fact, and I guess before we start we have to recall another fact, right? So the power series for this function is going to be this. So this is going to be our starting point. And now we're going to use that theorem and integrate. And on the left hand side we now have arctan x. On the right hand side we're going to have the constant of integration a, which is f of 0, which is in this case arctan of 0, which is 0, so we don't have to worry about it. And now we add the series obtained by term integration of the original series. So we're going to have negative 1 to the power n x to the power 2n plus 1 over 2n plus 1, and that's pretty much it, right? So we can also write out the first 5 terms. So when n is equal to 0 we have x. When n is equal to 1 we have x cubed over 3, and this is kind of the pattern. For the arctan function power series representation, and so on. Now, of course, this only makes sense on this interval of convergence, but however, when we integrate it, we may have included the boundaries. So instead of being concerned about that, let's just state that the center of convergence is 0 and the radius is still 1. And then we don't have to worry about whether it converges or not at 1 and negative 1. So we used the integration, term by term integration, once again, to find the power series representation of yet another function. All right, so the next and the last exercise will be very similar to the one in the previous lesson, when we assumed that we know the power series of cosine, and then we used it in the term by term differentiation to find the power series for sine. So we know this is the correct answer. And what I want to do now is I want us to use, instead of a term by term differentiation, I want us to use actually the integration. So to do that, again, instead of differentiating negative cosine to obtain sine, we're going to integrate just cosine to obtain the sine function. And let's see if it's all going to work out. And if it does, then we should be actually amazed how this power series were able to preserve these nice properties of trigonometric functions, such as derivative of sine is cosine, and derivative of cosine is the opposite of sine. So if power series can indeed preserve those features, then power series are doing a good job of representing functions. So let's give it a try. We're going to integrate, so let me just wipe this off. I will keep the final answer for us to check our work, but other than that, we will produce a new statement. And all right, so the integral of cosine of x is sine. The integral of the right hand side, we're going to have a constant of integration a, which is going to be the derivative, the function evaluated at 0, so it will be sine of 0, 0. So once again, we don't have to worry about this constant of integration. And here we're going to integrate term by term. So n is going from 0 to infinity, and here I'm just going to do exactly that, right? So we're going to now it goes raised to the power, so we're adding 1 to the power, and we're dividing by that number right over here. And using the properties of factorials, we can simplify that expression. And I don't know if you already see it, but there are so many, I mean, it shouldn't be too hard to see that what we have here is actually exactly the same thing that what we have here. So we again confirmed that if again what we assumed to be true at the top was indeed true, then the power series of sine should be this. And if we had any doubts before, now we shouldn't have any doubts. We were able to identify this power series of sine in two different ways, one using term-by-term differentiation and one's using term-by-term integration. So in this lesson, we'll learn how to integrate power series term by term, and by doing this, we can find power series of many other functions that we didn't know before.